Yes.
Hello, everyone. Welcome to the next session of MACSMIN, Mathematics and Computer Science for Materials Innovation. It's a pleasure to introduce Artur Bille from the University of Ulm in Germany, who will talk about random eigenvalues of graphenes and the triangulation of the plane. Over to you.
Thank you
Artur.
very much, Mr. Colin. And even more, thank you very much in advance for your attention to listen to what I want to tell you about our project, which is a part of my PhD thesis. My PhD thesis is supervised by two professors. One may be known, at least for Mr. Colin, Viktor Buchstaber, and the second one, Evgeny Spodarev. And during our work, I got in contact with two very interesting mathematicians in Paris, Simon Koste, and in Japan, Tokyo Satoshi Koriki. And we all together came up with this results I want to present you today. So I want to tell you a little bit about random eigenvalues. So maybe this term is not that familiar. So therefore I will introduce it and explain why we came up with this term, and also how to use it for graphene and its dual graph, the triangulation. So first, let me start with a short introduction, how we came up with this. At the beginning of our research, we started to analyze fullerenes. Fullerenes are originated in chemistry. For example, in 1996, the three professors Curl, Kroto, and Smalley got awarded with a Nobel Prize in Chemistry for synthesizing the fullerene looking like the polytope you see on the left-hand side of a picture. But they only synthesized one fullerene. And starting from then, so when they got awarded with the Nobel Prize, a lot of attention got viewed on these fullerenes from different fields of, for example, physics, chemistry, obviously, engineering. So how can you use these fullerenes for new materials? And also, of course, mathematicians. Because these fullerenes, they look, mathematically speaking, they are very easy to explain, but they contain a lot of interesting results of mathematics. And one very early result of mathematicians was, well, nice, you found one of the fullerenes, but we can prove that theoretically there are infinitely many. And it turns out that after a few years, new fullerenes were indeed synthesized. So the hypothesis, or the theoretical result of a mathematician was then proved to be right even in the real world, if you want to say. So as you can see, theoretically, fullerenes came up in different sizes and different shapes. But they have all in common three properties. The first one, that, and this is the definition of a fullerene, that they are simple, meaning that every vertex of a fullerene is connected to exactly three other vertices of a fullerene. Secondly, it's a convex polyhedra, meaning a three-dimensional polytope. So it must be convex. And the third and very important property is that the surface is divided into pentagons and hexagons only. And given these three properties, mathematicians work with these fullerenes very intensive. And very closely related to fullerenes is another carbon molecule, the graphene. which is a cutout or infinitely large lattice. And with two guys, Game and Novoselov, got awarded also with a Nobel Prize in physics for isolating these sheets of graphene. So graphene and fluorines have some similarities, but also some differences. For example, as you can see on this picture, the vertices are also, the graph, if you want to say, is simple, meaning that every vertex is connected with three others. The difference, important one, is that there are no pentagons, only hexagons, except the outer face, of course, but this is kind of error face. So, and these lack of pentagons converge, transforms the spherical fullerene, three-dimensional cage-like, to a flat two-dimensional one. And this idea of similarities and differences between fluorine and graphene, we will come up in a second. But first, let's jump back to fullerenes and derive some properties of fullerenes. So if we denote by n the number of vertices of a fullerene, the natural question is, okay, how many faces do we have? Well, we can say that the number of hexagonal faces is a linear function in n. The number of pentagons, on the other hand, is fixed. So we have, for any number of vertices, we have to have 12 pentagonal faces, not less, not more. Otherwise, we would not get a fullerene. So one of the definitions would get a contradiction. Then, what happens if you fix the number of vertices n? How many ways are there to interchange pentagonal and hexagonal faces on the surface such that you get a new fullerene with the same amount of vertices? And by different here, we mean non-isomorphic. Well, this question is still unsolved. We don't have a closed formula for the number, but we know it's finite for a fixed n. But then the question is, what if n, or what are the restrictions on n? And you can show that n must be an even number, which is at least 20, but it's unbounded from above. So for any even number greater than 22, actually, 22 is the only example where there's no fullerene. For every even number, you get at least one fullerene. So in total, if you sum up along all n's, you have infinitely many fullerenes. So many questions arise, like, how do you distinguish between fullerenes? What properties do some fullerenes have or not? Can we group them somehow? Can we find an enumeration among these fullerenes? And to do so, we wanted to use spectral graph theoretical approaches. The beauty of fullerenes is, due to their free connectedness, you can easily find a way how to project this three-dimensional polyhedra onto the two-dimensional plane, and such that the connectivity between vertices remains the same and without any crossing of lines, such that you, in order to analyze the geometry and the combinatorial properties of a fullerene, you can just analyze the corresponding graph. And as seen in the talk before, we are also interested not in the graph, but also in the dual graph. And in this case, again, to the free connectivity of a formulae, of a graph, this dual graph is unique up to isomorphism. So, looking at what are we want to analyze of a formulae, sometimes it's better to analyze the direct graph, sometimes it's better to analyze the dual graph. And the way we analyze graphs is the following. So let's stay with the direct graph. If we choose any vertex of this graph and we compute and we give for a given number of steps, let's denote it by k, we count how many closed paths can we find on this graph starting at and finishing at this specific vertex. And these closed paths contain a lot of information about the geometry or connectivity of this graph. For example, the easiest one is if k is equal to 2. Then the number of closed paths for any vertex is just the number of edges adjacent to this vertex. So it's the degree of a vertex. In the direct graph, it's easy. Every degree is 3. So the number of closed paths is 2. But in the dual graph, again, you get information, okay, if the number of closed paths of length 2 is 5, then we have degree 5. So this vertex corresponds to a pentagon in the direct graph. And the same works with 6, or the hexagonal faces. And you can do this for any vertex in the graph. And to sum up this information, we came up with computing the average number of closed paths on a formulae. And this number of this average number of closed paths we denote by μk of Fn, where Fn is some given formulae or some graph with n vertices. And then with very basic linear algebra knowledge, you can derive that this number can be written also as the kth power of the adjacency matrix, which uniquely describes the graph, and then taking the trace of this, so summing up the diagonal entries, and dividing this by the number, so you get the average number of closed paths. But this trace is nothing than the power sum of the eigenvalues of this adjacency matrix. And therefore, and because this sum looks like the mean value of the kth power of eigenvalues, we came up with a term of random eigenvalue. If you give to any of the n eigenvalues the weight 1 over n, you can interpret this as a distribution, an empirical distribution. And then we say a random variable of a graph or of a formulae is a random variable which has the following cumulative density function given here below. In our first article with Buchstaber and Spodarev, we actually analyzed these traces of a to the power k very intensively for formulaes. From a graph theoretical point of view, this analysis of the eigenvalues of a graph is a very important question. Maybe someone of you heard the question or read about what graphs are uniquely determined by their eigenvalues. And this question is still open. There are many examples where well, you have two non-isomorphic graphs, but they have the same eigenvalues. On the other hand, you have also families of simple graphs where this equivalency between being isomorphic and sharing the eigenvalues is equivalent. So you have counterexamples and you have positive examples. And in our first article, we made a conjecture, because it's very hard to prove, indeed, that for specific matrices and specific graphs or subgraphs of fullerenes, these subgraphs are uniquely determined by the eigenvalues. But in our current work, and what I want to present to you today, is the following question: what happens actually if n, the number of vertices, tends to infinity? So,
Artur,
yeah,
could I ask a
yes.
question about the previous slide,
Yeah, sure,
the
sure.
formula? So very nice formula. Does it work for all positive k, even for k equal to 1?
You mean the first one here?
Yes.
Yes, this works for, yes, it works for 1, because, well, you can think if a to the power 1 is just the adjacency matrix, and on the diagonal you have zeros. So this will be 0. And if you look at the graph again, well, starting from, for example, here, or even in the dual graph, you have no closed paths with length 1.
By length, you mean the number of vertices?
Yes, yeah, number of edges, yes.
Number of edges.
I mean, a closed walk or closed path of length 2 would be starting in this central vertex, going to this one and coming back. So we have 2 edges, a sequence of edges.
So they could have common self-intersecting edges.
Yes, 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 yes.
I see.
Mm-hmm.
Okay, yeah, thank you.
Yep.
Thank you, Artur.
Yeah, so the question was, well, if we if n tends to infinity, meaning that we get more and more vertices in our fullerene, and if we remember what we saw in the beginning about the properties of a fullerene, we know that the number of pentagons is fixed to 12, but the number of hexagons grows with n. So if n goes to infinity, we get more and more hexagons in our fullerene. And the question then arises, how does this, in some sense, limit graph look like?
So, Artur, can I just check? So I
Yes.
may have missed something here. You said the fullerene for Fn. Does that mean that, because there are several possible fullerenes, or is there only one possible fullerene for each n, or is there only one graph regardless of fullerene?
So this, okay, maybe I said it wrong. So I said the number for a fixed n, the number of fullerenes is finite. Usually it grows with n. So asymptotically, you can say that the number of non-isomorphic fullerenes for a fixed n grows approximately like n to the power 9. So it's still polynomial, but it's still also growing fast. And so for a fixed n, you have many fullerenes, but finite many. And for every fullerene, you have actually just one graph. I mean, of course, you can project it in a different way, but the new graph will be with isomorphic to the very first one. Does it answer your question?
Okay, so in that case, when you're talking about what happens to the adjacency matrix, there are going to be n to the 9 different adjacency matrices.
Yes,
look at.
About, yeah.
Okay.
Yeah.
So at each n. So when you say when later on you say what happens as the fullerene grows, what you actually mean is the set of fullerenes.
Yeah. What I mean, what the fullerene goes, it's a good question. Good point. This is what I will come in a minute about, because if you say we fix n and we choose, let's say we know somehow how to choose randomly one of these fullerenes with uniform distribution. And if you choose one randomly and you construct by this a sequence of fullerenes, of growing fullerenes, kind of a sequence of random fullerenes. The question is then, does this sequence have a specific limit graph?
Okay, so in other words, like the infinite fullerene is one fullerene, and yeah, or is it many? Okay, all right, I think I get it.
But I will get to that in a minute. And
thank you.
The second question then is, well, if n tends to infinity, how do we define a random eigenvalue for this? Because we don't have a real empirical distribution anymore. We have to define it in another way. And this third question, if we assume that we know how the limit graph looks like, and if we know how to define the random eigenvalue of this limit graph, can we say something about the distribution of that, or the properties, or whatsoever, maybe closed form of the density or whatsoever? So this is the main point of interest for us, to find this random eigenvalues and to derive properties. So now I come back to the point about the limit graph. Well, if you consider all fullerenes together, you will see that there are two important classes of fullerenes. The first one are the so-called nanotubes, meaning that you have a tube body consisting of hexagons only, and with two caps with 6 pentagons on both ends. And if you now increase if you take a sequence of nanotubes and you increase just the number of, or you can construct a sequence of nanotubes where n grows the number of vertices, therefore also the number of hexagons. And then still in the infinite case, you will get an infinite light nanotube, but this is not looking like graphene, for example. On the other hand, if you take spherical fullerenes, sometimes they are called Goldberg fullerenes or Goldberg-like fullerenes. They are spherical, and the important thing is the pentagons on the surface are uniformly distributed, meaning that the distance between the graph distance between the pentagons is always the same. And in between these pentagons, you will get an area which looks locally like like graphene, the hexagonal lattice. You have a flat area only of hexagons, where on with the nanotubes, you have also kind of a graphene, but rolled up to a tube. So the question is, if we choose randomly fullerenes, or we construct a sequence of random fullerenes, it's still not answered whether this will converge to a nanotube or to a Goldberg-like fullerene or something in between, maybe nothing of both. We cannot answer on that. We have numerical indicators which show that probably it will be more like Goldberg fullerenes. And this is what we assumed then in our paper. So we said that the limit graph of any fullerene looks with a probability of 1 as the hexagonal lattice or as graphene. So therefore we have to define what is a lattice. By lattice we mean here an infinite graph, meaning that we have infinitely many vertices, but every degree, the degree of every vertex is bounded, so finite. And the faces of the graph are regular convex polygons. And two important, or the two lattices we consider here is first of all the hexagonal lattice, but because we thought this is, or we assume that this is our limit graph, and the number of the set of vertices can be described in this Euclidean way as vectors in R2 with three parameters, x and y being integers and c equals 0 or 1. And if you take a look on this vector, you see that c is nothing else than a shifting vector +1 or 0. On the other hand, if you consider the dual lattice of H, as we saw it with fullerenes, it's the triangular lattice, and the set of vertices of this can be easily described using the vertices of H, just setting C to be equal 0. In other words, you could also say that the set of vertices of H is the same as two sets of vertices of T, but one set is just shifted by 1, and that's it. And in this illustration, you can see what I mean by that. So you see the hexagonal and triangular lattice overlapped. Vertices, which are colored red here, are the vertices where C is equal to 0, and the blue ones have C equal to 1. And we can derive some remarks from this illustration about the number of closed paths on a lattice. First of all, because we considered before the average number of closed paths, in this case, in the case of our regular lattices, the average number of closed paths is equal to the number of closed paths of any vertex of a lattice. So the number of closed paths of a red vertex is equal to the number of closed paths of a blue vertex. I see no. Okay. Should I check the chat now or skip it for later?
Artur, I asking if there are any questions.
Because I see there's. Oh, sorry. Okay. So the number of closed paths on the hexagonal lattice corresponds 1-to-1 to the closed paths on a triangular lattice. For example, if you choose the origin as the starting point and you want a closed path of length 4 on your hexagonal lattice going up to the right and going back, this corresponds to a closed path on the triangular lattice of length k, or of 2 in this case, going from here there and coming back. So therefore, if we count the number of closed paths on H and T, we have a simple and easy to compute relationship between them. This is what you should always keep in mind. Therefore, if I speak about H, it's easily can be transformed to T. Oh, sorry. So we define in this case of a lattice the random eigenvalue of a lattice as a random variable, such that the law of this or the moments of this random variable correspond or are equal to the moments or to the number of closed paths. So actually we define the random variable via the moments. And we will denote these eigenvalues of our two lattices by H and T. And the question, and the question is now, can we construct such a random eigenvalue for our lattices? And what we did to do so was to compute or to compute this number of closed paths. And there are many well-known formulas for that. And the one which fits our purpose is the following one. You can write this number of paths as a triple integral, each going from 0 to 2 pi, normalized by 2 pi for each of them. And then you integrate over the sum of these unit vectors or unit complex numbers, the sum of them, then taking the length of it raised to the power 2k. But this is very nice for us because this integral can be easily translated in terms of random variables. Because if you consider a random walk starting in the origin, where every step is equal to the step before, the position of a step of this random walk is the position of the step before plus one unit vector where the angle is uniformly chosen from 0 to 2 pi. So we do 3 steps of this planar flight, if you like, and compute the distance of the endpoint of this random walk and the starting point. And then you can say that these closed paths are equal to the 2k moment of this random variable. And these random variables are in stochastics very well known. There are closed formulas for the density and properties derived for them. And using this idea, we can derive a density for our wanted random eigenvalues. We can say that the random eigenvalue of the hexagonal lattice has the following density, which is an infinite integral over the Bessel function J0 and J0 to the power 3, where the Bessel function is defined as such a series. And for numerical reasons, reason, this second formula using the hypergeometrical function is much more convenient. It's much easier to compute than this infinite integral. So if we want to work with the message here is, if we want to work with random eigenvalues of a lattice, then we have also to know how to work with Bessel functions. And if we want, before starting working with them, I want to illustrate you how this density looks like for the hexagonal lattice. It has a finite support from -3 to 3 with 2 logarithmic poles at -1 and +1. And it's 0 at 0 for x equal to 0. And the same idea with relationship between h and t, with a relationship between the number of closed paths on h and t, we can modify this density for the case of a triangular lattice and get a very similar form, where the big difference now is that x has another support, which will be explained in a second. So the support changes from -3 to 3 to 0 to 9, which follows from the following, because you can describe the connection between h and t by taking the square root of t and multiplying by a. You get the same distribution as h, and vice versa. You can rewrite this formula for t also. So we have a very nice relationship between h and t in interpretational of closed paths, and also mathematically in distribution. And the density of t looks like that. So it's actually it looks very similar to h, but it's flipped only on the positive half line, and it's stretched to 0 to 9. And when we want to work with these densities, so we want to derive properties of it, characteristic function, whatsoever, integrability of characteristic functions, these infinite integrals are not that very handy. Therefore, we asked, well, how can we modify or simulate this distribution t? And if you recall the formula I showed before, so as this triple integration, and rewriting these exponentials as cosine plus I times sine, so the Euler representation, you can compute these sines and cosines, and you will get to something like that the random variable t is in distribution equal to the sum of 3 cosines scaled by 2 and shifted by 3. And the interesting thing is the arguments of these cosines. So we have differences of 3 IID uniformly distributed random variables on the interval 0 to 2 pi. So we transform this very complex random variable to a very basic one, but still properties of this of a right-hand side are also not easy to derive, because, for example, it's hard to if you just know the right-hand side, it's hard to derive a density and so on for this new random variable. Therefore, we asked ourselves, well, how can we simulate or approximate these differences of U1, U2, U1, U3, and so on? And then this is one of our main results in our paper is the following. If you say you have a random variable xb, just one, not 3 as before, which is uniformly distributed on the interval 0 to b, and we take any irrational number beta, and we construct a random variable yb, very similar to what we have seen before, as the sum of 3 cosines, where we have cosine of xb, cosine of beta xb, and cosine of the sum of the arguments before. So xb plus beta xb. And with the very same scaling and shifting as before, so multiplying by 2 and shifting by 3, and now letting b go to infinity, we see that this random variable converges to t. And in the same way, we can rewrite this for h. Before I come to the idea of the proof of this theorem, I want to give a small illustration of this convergence. So what we did was the following. We for a given number of samples, we simulated the left-hand side and compared the normalized histograms with the with the density of the right-hand side. And I hope you can see it on your screen well, that the red line here is the density function of ft, and the blue shadowed area, these are the bars of the histogram of our simulation. And then we just changed b from 1 up to b to 10,000. And what we see here is the following. For small b's, you have more or less flat area here and a peak on the right-hand side. In some way, it looks already not that bad, as if you compared with the right part of the red function. If b now increases, what you get is this pattern of flat body and then curve repeats and overlaps, such that with increasing b's, you get more and more smaller peaks, and at the end, this converges all to our density function ft. In the last 5 to 10 minutes, I want to give a very brief outline how we proved this approximation. And the very important thing is to note that the support of a distribution is a compact interval. Therefore, it's enough to show the convergence of moments. So we have to show that the moments of our constructed random variable converges to the moments of t, which can be denoted as this very beautiful sum of the squares of multinomial coefficients. The number of the moments of h look almost the same, just without this factor 2. So what we did is we took the left-hand side, we expanded this using the binomial theorem, then plugging in the definition of yb and using the multinomial theorem. Then you can come up with a very large, not beautiful sum, which I will show on the next slide. And in this sum, you will get a lot of integrals of the following form. So you have the limit of this normal or this integral from normalized integral from 0 to b, where you have a multiplication of a product of three cosines. And again, the same way, you have x, beta x, and the sum of the first arguments. And each of them is multiplied with an integer m1, m2, and m3. And only in the case that all of them coincide, you get for this integral the value 1/4 and 0 else. This makes this is how you treat this limit and this irrational number beta. And if you plug that into the left-hand side before, you will come with these three terms of sums, which you somehow have to simplify to this elegant sum of squares of a multinomial coefficients. This was a very this was the technical part of our proof, and we came up with an idea to compute the generating functions. So we computed the generating function for each of the sum you saw on the previous slide. And we compared this with the generating function for the right-hand side of what we have to show. And then we compared them, and it turned out that the generating function coincide, therefore the sequences coincide. And as a very important side result of this comparison of generating function, we came up with a very interesting equality for the modified Bessel functions, where you have the infinite, on the left-hand side, the infinite sum of the modified Bessel function, which are defined as this, the third power, and summing up over all orders of this Bessel function. And this infinite sum coincides with the infinite integral of the modified Bessel function to the power of 3. So this was the technical part of our paper. We are in the stage of finalizing it. I hope we will get it done until the next week. So next week probably it will, I hope so, will be on archive available. And for today, I would like to say thank you. Here are the main 3 references for this talk, and thank you very much for your attention. And if you have any questions, I would like to hear and try to reply to them.
Thank you, Artur. Thank you for your talk. Okay, I'm stopping the recording.
Mm-hmm.
And